The National Electrical Code, or NEC, requires that the grounding electrode conductor, also known as the GEC, be a continuous length of either copper or aluminum wire without any splices or joints. This grounding electrode conductor connects the electrical panel to the grounding electrodes, which typically include the footing, the cold water pipe, and the ground rod. The purpose of the grounding electrode conductor is to provide a low resistance path for fault currents to flow back to the source. This protects people and property from electrical shock and fire hazards. A continuous grounding electrode conductor ensures that there are no weak points in the grounding system that could compromise its overall effectiveness. Some may argue that it is acceptable to cut the grounding electrode conductor and splice it together using a listed ground log, but this is not in accordance with NEC. A ground log is not a suitable device for splicing the grounding electrode conductor, as it does not provide a secure and reliable electrical connection. The grounding electrode conductor must be a continuous piece of wire from the grounding electrode to the panel ground bar. It cannot be cut or spliced in any way. The NEC is very specific about how grounding and bonding should be implemented to ensure electrical safety. Firstly, let's define some key terms. Grounding refers to connecting the electrical system to the earth. This provides a reference point for voltage and helps to stabilize the system. Bonding, on the other hand, involves connecting various metallic parts of the electrical system together to create a low impedance path for fault current. The grounding electrode system, as mentioned earlier, typically includes things like ground rods, metal underground water pipes, and concrete encased electrodes, sometimes called a U for ground. The grounding electrode conductor connects the service equipment, that is, the electrical panel, to the grounding electrode system. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. It is critical that this conductor be sized correctly to handle potential fault currents. The NEC also specifies the acceptable methods for connecting to grounding electrodes. For example, when connecting to a ground rod, the connector must be listed for direct burial. Similarly, when connecting to a metal water pipe, the connection must be made within 5 feet of the point where the pipe enters the building. The requirements for bonding metal water pipes are also very important. In addition to the grounding electrode conductor connection, the metal water pipe must also be bonded to the service equipment enclosure, the grounded conductor at the service, and the grounding electrode conductor, if of sufficient size. This ensures that the water pipe is at the same potential as the rest of the grounding system, preventing electrical shock hazards. The NEC also addresses the use of supplementary grounding electrodes. These are often used in addition to the primary grounding electrode system to improve grounding performance, especially in areas with high soil resistivity. However, it is important to note that supplementary grounding electrodes are not a substitute for the primary grounding electrode system. They are intended to augment it. When installing grounding and bonding systems, it is essential to follow the NEC requirements carefully. Failure to do so can result in electrical shock hazards, fire hazards, and equipment damage. It is also important to use listed equipment and materials that are suitable for the application. Listed equipment has been tested and certified to meet safety standards, providing assurance that it will perform as intended. The NEC is updated every 3 years to reflect changes in technology and industry best practices. It is important to stay up to date with the latest version of the code to ensure that your electrical installations are safe and compliant. Local jurisdictions may also have additional requirements that must be followed. Always check with your local electrical inspector to determine the specific requirements in your area. Grounding and bonding are critical components of a safe and reliable electrical system. By following the NEC requirements and using listed equipment and materials, you can help protect people and property from electrical hazards. Remember that electrical work should only be performed by qualified and licensed individuals. If you are not comfortable working with electricity, it is best to hire a professional electrician to do the work for you. They have the training, experience, and equipment necessary to perform electrical work safely and correctly. In addition to the grounding electrode conductor, the equipment grounding conductor, or EG, also plays a vital role in electrical safety. The equipment grounding conductor provides a low impedance path for fault current to flow back to the source, tripping the circuit breaker or fuse and de-energizing the circuit. The equipment grounding conductor is typically a green or bare copper wire that runs along with the circuit conductors. It is connected to the grounding terminals of receptacles, switches, and other electrical equipment. The size of the equipment grounding conductor is determined by NEC Table 250.122, based on the size of the overcurrent protection device protecting the circuit. It is critical that the equipment grounding conductor be sized correctly to handle potential fault currents. The NEC also specifies the acceptable methods for installing equipment grounding conductors. For example, the equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the ground fault path is minimized. The NEC also addresses the use of metal raceways as equipment grounding conductors. In some cases, metal raceways, such as conduit, can be used as the equipment grounding conductor. However, the raceway must be properly installed and maintained to ensure a reliable electrical connection. The NEC also has specific requirements for grounding and bonding in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. In these areas, special precautions must be taken to prevent explosions and fires. The NEC requires the use of explosion-proof equipment and wiring methods in hazardous locations. The grounding and bonding requirements are also more stringent in these areas. Static electricity can also be a hazard in certain environments. Static electricity can build up on non-conductive materials, such as plastic or rubber. When these materials come into contact with a conductive object, a static discharge can occur, potentially causing a spark or explosion. To prevent static electricity hazards, the NEC requires bonding of non-conductive materials to ground. This helps to dissipate static charges and prevent static discharges. Surge protection is another important aspect of electrical safety. Surges are transient overvoltage events that can damage sensitive electronic equipment. Surges can be caused by lightning strikes, utility switching, or other events. The NEC recommends the use of surge protective devices, or SPDs, to protect electrical equipment from surges. Surge protective devices are typically installed at the service entrance or at individual branch circuits. They divert surge current to ground, preventing it from damaging electrical equipment. The NEC also addresses the grounding and bonding of sensitive electronic equipment. Sensitive electronic equipment, such as computers and medical equipment, can be susceptible to damage from electrical noise and interference. The NEC recommends the use of isolated grounding systems for sensitive electronic equipment. Isolated grounding systems provide a separate grounding path for the equipment, minimizing electrical noise and interference. The NEC also addresses the grounding and bonding of swimming pools and spas. Swimming pools and spas are particularly hazardous environments due to the presence of water and electricity. The NEC requires extensive grounding and bonding to minimize the risk of electrical shock in these areas. All metal parts of the pool or spa structure, as well as any electrical equipment associated with the pool or spa, must be bonded together and connected to the grounding system. Ground-fault circuit interrupters, or GFCIs, are also required for all receptacles within a certain distance of the pool or spa. GFCIs are designed to detect ground faults and quickly interrupt the circuit, preventing electrical shock. The NEC also addresses the grounding and bonding of recreational vehicles, or RVs. RV are essentially mobile homes with electrical systems. The NEC requires that RV be grounded and bonded in accordance with specific requirements. The grounding and bonding requirements for RV are similar to those for homes, but there are some additional considerations due to the mobile nature of RV. The NEC also addresses the grounding and bonding of boats and marinas. Boats and marinas are also hazardous environments due to the presence of water and electricity. The NEC requires that boats and marinas be grounded and bonded in accordance with specific requirements. The grounding and bonding requirements for boats and marinas are similar to those for swimming pools and spas, but there are some additional considerations due to the marine environment. The NEC is a comprehensive document that covers all aspects of electrical safety. It is important to understand the NEC requirements and follow them carefully when installing and maintaining electrical systems. Electrical work should only be performed by qualified and licensed individuals. If you are not comfortable working with electricity, it is best to hire a professional electrician to do the work for you. The proper implementation of grounding and bonding is not just about compliance, it's about saving lives and protecting property. A well-designed and installed grounding system provides a safe path for fault currents, minimizing the risk of electrical shock, fire, and equipment damage. Neglecting or improperly implementing grounding and bonding can have serious consequences, putting people and property at risk. Therefore, it is crucial to prioritize grounding and bonding in all electrical installations and to ensure that the work is performed by qualified professionals who understand the NEC requirements. We remember that electricity is a powerful force and it must be treated with respect. By following the NEC and using common sense, you can help ensure that your electrical system is safe and reliable. In summary, always ensure the grounding electrode conductor is continuous and unspliced, that all connections are made with listed hardware, that equipment grounding conductors are properly sized and installed, and that surge protection is in place when needed. Regular inspection and maintenance of your electrical system is also recommended to identify and correct any potential grounding and bonding issues. Education and awareness are also key to promoting electrical safety. Share this information with others and encourage them to learn more about grounding and bonding. By working together, we can create a safer electrical environment for everyone. The NEC is constantly evolving to address new technologies and challenges. Stay informed about the latest updates and revisions to the code, and make sure your electrical installations are compliant with the current requirements. The NEC is not just a set of rules, it is a guide to safe electrical practices. By following the NEC, you are not only complying with the law, but also protecting yourself and others from electrical hazards. Grounding and bonding are not just theoretical concepts, they are practical measures that can save lives. Take the time to understand the principles of grounding and bonding, and apply them diligently in your electrical work. Your efforts will make a difference. Always remember to consult with a qualified electrician for any electrical work that you are not comfortable performing yourself. Electricity is a dangerous force, and it should be handled with care and respect. A qualified electrician has the training, experience, and equipment necessary to perform electrical work safely and correctly. They can also help you ensure that your electrical system is compliant with the NEC and local codes. So, when in doubt, call a professional. It is always better to be safe than sorry. The continuous and unspliced nature of the grounding electrode conductor is paramount for several reasons. Firstly, a continuous conductor provides the lowest possible impedance path for fault current. Any splice or joint introduces resistance, which can impede the flow of fault current and delay the operation of overcurrent protection devices. Secondly, a continuous conductor eliminates the risk of corrosion or loosening at splices or joints. Over time, corrosion can degrade the electrical connection, increasing resistance and reducing the effectiveness of the grounding system. Loosening of connections can also occur due to vibration or thermal cycling, leading to the same problems. Thirdly, a continuous conductor simplifies inspection and maintenance. It is easier to visually inspect a continuous conductor for damage or corrosion than it is to inspect multiple splices or joints. This makes it easier to identify and correct potential problems before they become serious. In addition to the continuous conductor requirement, the NEC also specifies the type of connectors that can be used for connecting to grounding electrodes. The connectors must be listed for direct burial and be compatible with the materials of the grounding electrode and the grounding electrode conductor. For example, when connecting a copper grounding electrode conductor to a galvanized steel ground rod, a connector that is listed for use with dissimilar metals must be used to prevent galvanic corrosion. Galvanic corrosion occurs when two dissimilar metals are in contact in the presence of an electrolyte, such as moisture. The more active metal will corrode, weakening the electrical connection. The NEC also requires that the grounding electrode conductor be protected from physical damage. This can be accomplished by installing a conductor in a raceway, such as conduit, or by using a listed cable assembly that is designed for direct burial. The protection from physical damage is important to prevent the conductor from being cut, abraded, or otherwise damaged, which could compromise the integrity of the grounding system. Furthermore, the routing of the grounding electrode conductor is also important. The NEC requires that the grounding electrode conductor be run in as straight a line as possible without any sharp bends or kinks. Sharp bends or kinks can increase the impedance of the conductor and reduce its effectiveness. The NEC also prohibits the use of the grounding electrode conductor as a support for other equipment or wiring. The grounding electrode conductor should be dedicated solely to the purpose of grounding and should not be used for any other purpose. This helps to ensure that the conductor is not damaged or overloaded, which could compromise the grounding system. In addition to the grounding electrode conductor, the bonding of metal enclosures and equipment is also critical for electrical safety. The NEC requires that all metal enclosures and equipment be bonded together to create a low impedance path for fault current. This is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal parts together. The size of the bonding jumpers is determined by NEC Table 250.102, based on the size of the circuit conductors. It is important to ensure that the bonding jumpers are properly sized and installed to provide a reliable electrical connection. The NEC also addresses the bonding of metal water pipes. As mentioned earlier, metal water pipes must be bonded to the service equipment enclosure, the grounded conductor at the service, and the grounding electrode conductor, if of sufficient size. This helps to ensure that the water pipe is at the same potential as the rest of the grounding system, preventing electrical shock hazards. The NEC also requires that the bonding connection to the water pipe be made within 5 feet of the point where the pipe enters the building. This is to minimize the impedance of the bonding path. The NEC also addresses the bonding of other metal piping systems, such as gas pipes and sprinkler pipes. These piping systems must also be bonded to the grounding system to prevent them from becoming energized in the event of a fault. The bonding requirements for these piping systems are similar to those for metal water pipes. In addition to the bonding of metal enclosures and equipment, the NEC also addresses the grounding of sensitive electronic equipment. Sensitive electronic equipment, such as computers and medical equipment, can be susceptible to damage from electrical noise and interference. The NEC recommends the use of isolated grounding systems for sensitive electronic equipment. Isolated grounding systems provide a separate grounding path for the equipment, minimizing electrical noise and interference. The NEC also addresses the grounding of separately derived systems. Separately derived systems are electrical systems that are not directly connected to the utility power supply. Examples of separately derived systems include generators, transformers, and uninterruptible power supplies, or UPSs. The NEC requires that separately derived systems be grounded in accordance with specific requirements. The grounding requirements for separately derived systems are similar to those for service entrances. The NEC also addresses the grounding of high-impedance grounded systems. High-impedance grounded systems are electrical systems that use a high-impedance resistor to limit the ground fault current. High-impedance grounded systems are typically used in industrial applications where it is important to maintain continuous operation even in the event of a ground fault. The NEC requires that high-impedance grounded systems be grounded in accordance with specific requirements. The grounding requirements for high-impedance grounded systems are different from those for solidly grounded systems. The NEC also addresses the grounding of ungrounded systems. Ungrounded systems are electrical systems that do not have a direct connection to ground. Ungrounded systems are typically used in industrial applications where it is important to maintain continuous operation even in the event of a ground fault. The NEC requires that ungrounded systems be grounded in accordance with specific requirements. The grounding requirements for ungrounded systems are different from those for solidly grounded systems. The NEC also addresses the grounding of equipment in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. In these areas, special precautions must be taken to prevent explosions and fires. The NEC requires the use of explosion-proof equipment and wiring methods in hazardous locations. The grounding requirements are also more stringent in these areas. In addition to the NEC requirements, there are also other standards and guidelines that address grounding and bonding. These standards and guidelines can provide additional information and recommendations for designing and installing grounding and bonding systems. Some of these standards and guidelines include the IEE 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, and the ANSI C62.92, Guide for Application of Neutral Grounding in Electrical Utility Systems. These standards and guidelines can be helpful for understanding the principles of grounding and bonding and for designing and installing effective grounding systems. In conclusion, the grounding electrode conductor must be continuous and unspliced to ensure a low impedance path for fault current, prevent corrosion and loosening of connections, and simplify inspection and maintenance.